At this time, we present the result of our research developed under the supervision of Isabel Sacristán. This work is part of the design research project that aims to enhance engineering students' learning situation with the construction, design, and programming of video games. My name is Pretelín-Ricárdez. Okay. Our study is a design research where we seek to develop and refine our approach to develop principles that might guide future implementation. In the past 2 years, we have been involved in a project with last-year engineering students at the National Polytechnic Institute in Mexico. The design of activities and their implementation is framed in the constructionist educational paradigm, which considers that learning is facilitated through engagement in the construction of external objects. Each activity integrates 3 aspects: the mathematization of a physical or digital system, programming, simulation, and construction of video games. Here, students work both individually and collaboratively and record their progress in a logbook. With this approach, we want students to apply their mathematical knowledge in their model and video game construction, and in this way learn to situate or contextualize it, as well as relate it to other disciplines as is required in engineering in real life. This is a cycle of construction, the general research. The cycle of construction consists of a learning sequence with 3 activities: mathematization of a physical or digital system, programming simulation, and the construction of video games. This construction cycle is carried out as follows. In the block one, a realistic system or situation is proposed related to engineering. Participants will have to model this RSS for implementing it into the game mechanics of a video game. In the block 2, participants will need to identify the physical parameters in those realistic system or situation and describe them through algebraic formulas or equations. This is a first mathematical characterization. And the block 3, that first mathematization of the RSS will need to be converted into a working model in the game engine computer code in order to test it and validate it in a first simulation, okay, in the block 4, okay. Here are 2 possibilities. If the implementation does not work, then in the block 5, the model needs to be simplified or adjusted, abstracted again. It is abstracted again through the manipulation or computational objects and programming code, repeating steps 3 and 4. If simulation runs properly, then we have a modeling context here. Okay, that is ready for the final implementation in the video game. Okay? This is a theoretical framework, constructionist model eliciting activity. In this stage, we provide 4 examples of student designs during the first stage of the activity sequence, which correspond to the learning or familiarization with the game engine, Game Maker Studio, its physics engine, and its physics programming language. We ask students to design and implement experiments to characterize a set of basic physical parameters used in the game engine: density, restitution, friction, linear damping, angular damping, velocity, force, impulse, and acceleration of gravity. Okay. For this stage, the purpose of this is that during the design and implementation of experiments, students learn to relate the meaning of command or piece of code and other computational objects like sprite, background, sounds, with concept, mathematical or physical or mathematical equation in these blocks. Okay? By assigning objects with mathematical or physical properties, they can develop a video game where the correlation of meaning helps build more complex model. Okay. Okay, this is a list of experiments that we show in this presentation. The example one, the sonic bombs video game, the impulse and force, variation of physical parameters on different objects, Donkey Kong checking physical parameters of some object, and simple pendulum and control of an inverted pendulum. For the examples given in this presentation, the introductory stage was carried out over the course of 8 sessions of 1 hour and 30 minutes each. The examples correspond to 4 undergraduate engineering students in their final years, Jorge, Victor, Carlos, and Moises. During each session, the instructor had a facilitator, role solving a specific question or providing digital resource needed by the students. Students document their progress through logbooks, session students' interviews were video recorded. In the following section, we briefly describe some of the construction that the students created during their simulation of video game experiments for trying out the parameters that would be used in their final video games. This is the example one, the Sonic Bomb video game impulse. The objective of the video game is that I showed part of the storyboard of the student, and the objective of the video game is that the player must go from a starting point to an endpoint flag, where both points are separated by a gap of several meters. The way in which the player must move from one point to another is by jumping and flying using the impulse provided by concussion grenades. Concussion grenades are a type of grenade that explode after a certain time from activation, generating a sonic shock wave that will help the character increase their velocity, giving them an impulse to reach other places without generating damage. Okay, I showed the first implementation, a preliminary implementation of game of Jorge. It is okay, this is the first slide.
So did you understand it's a bomb, it's a sonic bomb, and that bomb throws the character across the gap?
This is a preliminary version of game. Other version that the video game final with other person or other character. This is a This is the sound of a bomb. The mathematical basis for this game are the Gorny equation. The Gorny equation are a set of mathematical formulas used in explosive engineering to relate how fast an explosive will accelerate a surrounding layer of metal or other material when the explosive detonates. This is a Gorny equation, and this is the basic principle that rules the video game, inside the video game. Okay, and this is a conclusion. Okay, the example 2. Variation of physical parameters on different objects. In this experiment, we want to observe the interaction between objects with different physical parameters Victor objects apply a gift box, motorcycle, a jeep car, and gem are shown in figure. For the experiment, Victor decides that the player object must change its physical parameters each time it collides with another object. That this player object will acquire the parameters of the object that it touches. It is one of the preliminary version of video game. It's, the movement.
He's saying that the movement here was still very chaotic, erratic. So it wasn't in this preliminary version of the student's video game.
And it is only a simulation of the parameters. In the previous case, it's a video game, but here it is only a simulation. It is a ball, touch, or other object that a car or gem or motorcycle or gift box. The mass, velocity, and inertia change. Okay. It is an experiment for only characterization of parameters. Okay. And in this case, Victor,
Victor had to characterize each of the parameters that was
okay.
So every time the ball touches an object, it acquires the characteristics of that object it touches. So that's what's happening.
Okay, the matter product of the characterization of the parameters that Victor make. Okay, for player, gift box, motorcycle, jeep, and gem density. The parameters inside this simulation is density, restitution, linear damping, angular damping, and friction. Okay.
And this table was actually the student actually recorded this table on his own in his logbook. So we actually just copied it from his book, from his diary that he was. And everything he did all himself.
Oh, the example 3, Donkey Kong, like checking physical parameters of some object. The student check the physical parameters of the objects, front ball, cannonball, and trunk. He will put these objects in an inclined plane to analyze how they will behave according to the density, size, shape, and friction generated between each other and with the environment. This simulation experiment was designed by Carlos. He assigned to each object physical parameters as in reality. He also designed a scenario composed of 4 ramps and starting point where objects are created and end point where object will be destroyed. Each ramp will be inclined 2 grades less than the previous one, starting from top to bottom with the first ramp as 10 grades. Therefore, the final ramp will only be 4 grades. The scale used is 1 meter equal. The scale used is 1 meter equal 32 pixels. The value of gravity acceleration was approximated than 10 meters over second square. Okay, this is a room of the Carlos analyzed the behavior of each object or particle with and his characters. In this case, don't have a collision within him or not there, between there, because
between the objects.
see.
So So the objects don't collide among each other.
para evitar colapsos.
And that prevents blockages. So that. And then here they touch each other. Oh, you mean they're independent, even though they can be on the same.
Okay, the thing by this simulation, and this is a simulation of simple pendulum and control of inverted pendulum. And a pendulum is a mechanical system that can be used to experiment with a relationship between several physical parameters and the acceleration of gravity. I run the simulation. The simulation experiment was designed by Moses. If the mass then we have an inverted pendulum, which is a system of unstable nature. This is a classic example for a study of automatic control. And here, Moses implemented only the model of classical pendulum and model and control by the inverted pendulum. Okay, he works a proportional control to balance an inverted pendulum using the following formula. Okay, the formula with Cape.
You can see it there.
Okay. Mention how much they appreciate these experiments, mentioning that they provide the only opportunity in the engineering study for actually simulating mathematical models as they would behave in real life. Other students comment regarding the appreciation of these experiments, like Moises and Victor. And when we do this experiment, we become aware of how many errors can occur in the construction of systems, programming errors and errors in assigning values due to the restriction of the physical engine. I felt a great satisfaction after being able to simulate and control a pendulum, because this showed that we can simulate any type of system in 2D, from a pendulum to robotic arms, which is helpful to visualize the behavior of the system without the need deep programming knowledge to create them. Even with the basic understanding and modeling of the system, we can create quite complex games. This activity, in the case of Victor, these activities were different. Here, you have a set of parameters to play with. You can perform an experiment and then another experiment with many parameters easily. This is faster, more accessible, and also fun to experiment. And on the other hand, from our perspective, it was very satisfying to see how students carry out each task with high level of involvement in something that was extracurricular. That satisfaction is even greater when we play with the simulation and video games that they create. Okay, and final remarks. With this activity, we explored and observed how the students, through their experimentation, can express a mathematical and physical meaning through programming codes or commands. We believe that this kind of experimentation can plant the seed of powerful ideas, which in this case will allow the construction of the mathematical modeling of more complex physical systems. In this way, the construction activity elicited new ways for students to apply the mathematical knowledge and gain experience in solving problems. Thank you very much.
Questions?
Yeah. Thanks for that. So a couple examples. They were not looking values up in some text. They were sort of tinkering and tuning those values of the properties of objects themselves, correct?
Yes, but not. And in another case, tuning or apply concepts.
Okay.
Yes.
So they had the formulas that they were working with. They were, for example, trying to drop the tennis ball and the cannonball, and they were sort of tuning those parameters to get it to behave like they felt it should. Is that correct? Or?
Well, they actually designed the whole thing
Right.
from scratch.
Right. Right.
So they had to, we showed it to, in Vienna, where they actually had, for instance, to simulate water behavior.
Right.
So they had the formulas, they had the two different models of water behavior,
Yeah.
and very complex. But then what we didn't show today, and maybe it was a mistake, is how it actually, then they have to identify what the different parameters in order to actually input them into the video game engine, and from them create the video game engine. Yes.
Really cool. That's really cool. I mean, I certainly when you build great, but you still have to sort of tune it to get the behavior you want. My question is I'm wondering to what extent they sort of bought it, right? To what extent they bought these activities that they were engaged in of tuning and of adjusting the values and of adjusting the parameters as sort of a legitimate mathematical exercises versus, how one makes games, right? Those might be the exact same thing.
No, actually-
Do they see it as
Oh,
the
yes,
same thing?
because these are last semester, about the time we sent the paper, I interviewed them, and they actually said to me, this is the first time I've had the chance to actually put into practice all the mathematical knowledge I knew,
Oh, nice.
and actually put it into practice, into something real
Right.
and concrete. Because before that, everything had been theoretical for them. They had the experience of actually putting into practice things. So all the mathematical models, for instance, the one for the water, they knew the mathematics, but then they actually had to simplify those mathematics in order to insert it into the video game engine, and to understand much better what was really important, and how could you simulate and really put it into practice in this particular context. And for many of them, every single one I interviewed, and I interviewed them separately, and I was really struck. I even told Anka,
Yes.
all of them told me the same thing. All of them told me this is the first time we've had a chance to actually do a real life. Many of them use the word, it was like a laboratory.
Right.
It was like really.
These are university students. Right?
University, yeah,
Sure.
last year
Yes.
university students.
Thank you.
So, English and microworlds. But
Yes.
it's not common to combine those. So, as a designer, did you find, can you say something about the process of combining those two theoretical?
Okay, it's in the the idea of microworlds was in terms of Celia Hooks and Richard Knowles definition that uses microworlds in terms of taking into account the entire context of learning. So the setting, the pedagogical interventions, the tools, it's the contextual aspect, the pedagogical aspect, the technological aspect, and the student access component. So we define that in using those terms. And then the LASH, the model of eliciting activities, we use the 6 principles.
No.
Do you have a slide?
Yes.
In order to design the actual tasks. So that's where that came in. So it would be, if we were integrating it into, it would be part of the pedagogical component of the micro world, would be where we were using those 6 principles.
Okay, this is
of-
the
Okay, those are. No, then it's not in this PowerPoint,
No,
sorry.
in-
No, porque first.
Sí, pues. No.
So it wasn't in this slide.
Yes.
Because we didn't present that to you.
Okay.
Any other questions?
Yeah. This student, when they were at the beginning and trying to use this mathematics that they had but never applied, the sort of mistakes that they made, and then how those got resolved as they actually worked through the building process. Is it possible to give an example?
Or by video recorder, and the session, all the session are okay, an example, for example, okay. There are an example in work in progress. For example,
I have a workshop this afternoon on this,
okay, yes.
so you can actually.
Okay, I'm sorry. Did you finish really answering Dave's question, or is it postponed? My question is, I remember hearing this talk a long time ago. This physics professor, I think he was at the University of Washington, he had his first year physics students make video games about what they were learning. And everything was perfect. The students just loved it. They learned their physics much better. They all said it was the greatest thing ever. And then he said he had to stop doing it. I asked him why, and he said, because all the other people complained that the students were putting 20, 30 hours a week building these games, and they didn't have time to study the other subjects. So I'm wondering, though, if there's any, did they have to, how much time did they have to put in to do this?
Well, this is a semester, they're all volunteers, and it's a semester-long course. So they have, 4 hours per week, 2 sessions of 12? 3 hours per week, where they are actually in the course, which is not really a course, it's more time with them to facilitate. And then they do put up a lot of time, and sometimes they do complain, oh, we ran out of time, we couldn't complete this because we had all this other work. Because they do give priority to their real courses, because they're not getting credit for this.
Yes, right.
They're just doing it as volunteers, which is very nice, but they actually love it, so.
Yeah.
Because they build a robotic arm, but the robotic government, the robots, okay, it's collide.
Collapses, yeah.
Collapse.
It doesn't really work.
And this problem is a work in progress in this moment, and they by solve this they.
No, I'm
So you
just
can
saying,
start
set
setting
up,
up
well,
the-
we do have to do a lot of, identification of what is wrong there. Does that sort of answer? your question?
It's an example.
Yes.
I don't know, we didn't show inside the game engine, I'm sorry.
Good, well, thank you
Yeah.
again.
But